All right, well, good morning, good afternoon to wherever time zone you are in. Thanks for having us here today. I am Dusty Jacobson. I am the Director of Process Engineering for Mining Crushers in Metso Autotech. With me today is Alan Boylston, and he's the head of process engineering on the grinding side for Metso Autotech. So we have most of the entire comminution chain covered between our two groups. Now, as we started looking at the agenda for this program of fines processing, one thing we wanted to touch on was how the entire circuit and comminution plays a role into getting to that final grind size and final liberation size. So what we're going to go through here today is looking at where the fines come from throughout the circuit, how they're produced at each one of the different stages, and how it all kind of ties together to make the most efficient way to get down to that final size. I do want to acknowledge Edison Nunez and Lucas, who helped out with especially site survey data for this presentation. So we're going to go through here just real quick as a real basic background into where are the fines coming from throughout the entire comminution chain, and how do the different types of comminutions create those fines, and how much of that proportion comes from the different stages of the comminution. So looking at the size distribution as we move from one end of the plant down to the final grind size, how much work is being done at each one of those stages, and how does that contribute to the overall work done in the plant. So to get into a little bit more of the detail of it, we have one case study that looks at a large copper mine going from the blast through the final grind size, where those fines are being generated, how they're being handled. And then we're going to get into more specifics on HPGR technologies and how they're being used to generate a lot of those finer particles, whether it's aiding in the ball milling process to make those fine products, or making those final products directly closed circuit with the HPGRs. So first off, let's just walk through really quickly the different types of comminution that are happening in the chain and how they relate to that fines production and how they get processed. Well, the first step is going to be blasting, and that's by drilling, putting explosives in, and that explosion within that rock bed then will fracture the particles and shear the particles out into smaller sizes. Now, the blast size distribution varies very greatly from one site to the next. Some sites have very fine blasts with a lot of fines content in them. Some have very coarse, very blocky type blasts. And it depends on the blasting strategy as well as the ore properties themselves. So there are some things you can do to influence that fines production at the blast, but there's usually going to be some type of limitation to it. And blasting by itself usually doesn't create a lot of the -300, -200 micron particles. There's been a lot of studies done about the fines production in these blasts, and a lot of them determine inflection points somewhere near that 1 millimeter larger or smaller range, that those blasts really have a good influence in the size distribution. In the mining side here, typically we have one type of crushing, and that's going to be compression crushing. Now, there is impact style of crushing, and we're not going to really discuss that too much here today because it's not predominant in the mining side. But it can be useful as generating finer products in certain applications with certain ore properties. And we start looking at single particle compression. So compression crushing can be broken into two basic types. One single particle, and that's where you take one rock, one particle, and you compress it between two surfaces, and you put a force into that particle. And if you look at it really on a microscopic level, what you're doing is you're taking that particle and you're trying to compress it smaller. So you're trying to decrease the width of that particle, and it's going to want to then mushroom out for the same volume. Then if the width gets smaller, it needs to spread out in that direction. Now, rocks are generally brittle, so as I try to spread out that rock, it's going to create tension between the grains and the different sections within the rock, and it's going to propagate a crack, and that's what's going to fracture the particle into smaller pieces. Now, if you look at single particle breakage, true single particle breakage, where you're just putting that force against one rock, typically what you'll see is you'll see that crack propagate right in between those two forces, and the particle will break down into maybe 2 particles, 3 particles, 4 particles. So it breaks down into very few particles that typically end up being fairly coarse. And single particle breakage is predominant for primary gyratories, for jaw crushers, and slow speed cone crushers, and even secondary cone crushers are predominantly that single particle breakage. Now, the next type of compression breakage is going to be packed bed or interparticle crushing. And that's where I have a bed of particles sitting between those two crushing forces. And as I squeeze that bed of particles closer together, I get very high pressure between the particles that are connected inside of that packed bed. And as I start to decrease that void space in between them. The particles don't have places to go and roll into, so the pressure gets high enough that they start to fracture. And the fracture in interparticle breakage and packed bed breakage is a little bit different than single particle breakage, because I'm putting that force 360 degrees around that particle. I can get multiple cracks propagating at different areas on that rock. So it tends to break down into more particles and smaller particles than single particle breakage does. And just through the natural act of compressing those particles together, you do get some level of shearing of the surface or attrition as you start to pack those particles and they grind away slightly against each other. Now, this is where HPGRs are really used for this packed bed breakage. It's almost 100% packed bed crushing inside of an HPGR. And if you look at a lot of the high-speed cone crushers, especially short head crushers, tertiary, quaternary pebble crushers, they operate usually with somewhere between 70 to 90% packed bed crushing inside of their chambers. So relatively less single particle breakage, more packed bed breakage with some of those high speed cones. So you start to get a finer product size and you're generating more of those smaller particles. And the last type, and the one that's really generating the most amount of these fines here, is going to be attrition or grinding. And that's where you're shearing or wearing away of the surfaces of the particles. So it's not necessarily impact breakage or fracturing the particles into smaller pieces. It's grinding the outside surface of those particles to generate those fines. And those are all the horizontal vertical mills that are used within a circuit. So we wanted to quantify somehow where the fines content was coming from. So if a plant has a generic final grind size of less than 300 microns, so P80 of 150, 200 micron, and they're grinding down to about 300 micron. Where does that 300 micron material come from? So that's an arbitrary number. This isn't something that was universal for all the plants that we reviewed. But we've done a number of site audits and surveys throughout the circuits. And you can see on here that we looked at 6 different sites. We had 17 total samples of the circuit. Especially there's a lot of variation after the primary crushing and after the blasting. So multiple samples were taking a look at where those size distributions were classified. 3 of the circuits looked at were traditional 3-stage crushing going to ball mills. So we could look directly at crushing circuits going to ball mills. And the other ones were 2-stage of crushing going to sag mill circuits. So sag mill with a pebble crusher. So primary stage of grinding and a secondary stage of grinding. And just as a note, that when I say 3-stage crushing, crushing does include HPGRs as well. So most of these were primary crusher to secondary cone to an HPGR as the 3rd stage of crushing on there. And you can see the size distribution in that graph over there. The green lines are all the size distributions after the primary. And for a primary crusher, typically it's all single particle breakage. We're not really contributing significantly to the amount of minus 10 millimeter or the minus 300 micron in the particle stream. So most of that is coming from the blast. We're really just knocking down that top size. You can see the red lines now is after that 2nd stage of crushing here. So after the 2nd stage of crushing, we are starting to make a finer product that's going to be going downstream, but we're not generating a huge amounts of the very fine particles like the 300 microns. You can see it's very similar after the 2nd stage compared to the primary stage and after the blast. Now, if you go a little bit further here, what you can see, the light gray line is after primary grinding with the sag mill. You can see now there's a significant generation of that 300 micron in that fraction. And then just one curve I put in after the ball mills just for representation was a significant amount of that minus 300 micron that was coming out. You can see 85–90% of it was minus 300 micron. So the vast majority of that fine product, that minus 300 micron product, was coming from the grinding stage. So why is it important to look at some of the secondary crushing stages? Well, that table that we have up here on top shows 2 different rows. One is the 300 microns, that's your final product size. And you can see here the ball mills were creating a significant portion of that 300 micron. The primary grinding with the sag mill was a very high portion. And there was actually relatively a little amount of the material coming from the blast, from the primary and the secondary crushers. And even when we start looking at the tertiary crushers, that minus 300 micron, the generation of it wasn't being significantly influenced by the crushing section of it. But another thing you want to look at is the efficiency of that grinding circuit. And we chose 10 millimeters because it's very close to a standard sieve size. And it's also a relatively important point for ball mills. So you don't want to have too coarse of a feed. You don't want to have large top size going to the ball mill. You have a drop off in efficiency there. So the more of that minus 10 millimeter that we can really crush down to, the more efficient the downstream is going to be. And that's where you see that the blasting can have a significant effect on that minus 10 millimeter. Primary crushing, not very significant, and even secondary crushing does generate a fair amount of minus 10 millimeter, but it's not a predominant goal of those crushers to crush down to minus 10. If you look at the tertiary crushing and HPGR, now is where we do the bulk of the work to get that material to that proper feed size going to the ball mills there. And just as a representation too, I also did pull some other data that was showing some measured blasts, so full surveys of the blast. And you can see the minus 1 millimeter that was shown in this table here from a study, and it ranges anywhere from 2% up to 18%. So 17% coal, very high fracture rate down to very fine particles. Most of them were at 2, 11, 5, 2%. Very little of that fines content, except for this porphyry copper ore, which was a copper plant with very high intensity blasting. So they were able to get up to 18% minus 1 millimeter in their blast, which I would consider to be kind of the optimistic high point that you can get for fines from those blasting points. Why are we talking about this? And really, when we look at all of that, you'd think the only thing that's important throughout the entire circuit would be the grinding mills, because that's where the majority of that final grind is coming from. But what we want to kind of consider now is that each one of the stages throughout that circuit has a role in getting down to the final product size. And some of the stages of comminution are much more efficient at getting to that reduction than grinding would be. So blasting, crushing, generally speaking, are going to be more energy efficient, and they're also going to have lower operating costs pretty significantly when you look at some of the case studies for these. So each one of the chains needs to be looked at together and related so that you can get the optimum way to get down to your final grind size. Because really what you're trying to do is get down to that fines particle, fines product as quick as you can and as cheap as you can in order to make your plant the most profitable. So what we're going to do here now is just look at a real quick case study on the entire chain from the blast all the way through the final grind and look at what they did to optimize that entire circuit here. So this is a very large copper mine in South America, very high tonnage plant. So it had gyratory crushing at the primary. It had cone crushing in the secondary and closed circuit. Went to HPGR in the tertiary crushing circuit, enclosed circuit, and then one single stage of ball mill to make the final product through there. So similar to what we had looked at in the historical review, you can see that the blast material has a small amount of minus 10 millimeters in here, about 10% minus 10 millimeter, but very little is going to be that very fine particles like 300 micron or less than 1 millimeter. It's only a matter of a couple of percent in that range. And even after the primary crushing, you can see here that we took that top size and we shifted it to the left. So we took that curve and we took the top size away from it, but we're not generating a significant amount of fine particles with the primary crusher. And you can see here that the size distribution converges away into the blast size distribution here after the primary stage. So primary crushing is not really going to be used to generate a fine product. All it's there is to knock down that top size so it can be handled by the downstream equipment, whether it's material handling and conveyors, or it's the next stage of crushing or sag mills after that. Now the secondary crushing we start looking at here, we can see that this blue line, which is the total circuit product that we were getting, is starting to generate more of that minus 10 millimeter product that's going to be good feed for the ball mill. But again, you see that curve converges here down on the fines fraction. So we're not crushing down to minus 300 micron with those secondary cone crushers by any significant fraction. In this case, it ended up being only 3% more compared to the feed that was going into the secondary stage. And like I said, secondary crushing most often is going to be single particle breakage. Single particle breakage is great for knocking down the top size, pretty good at knocking particles down to that minus 10 millimeter, but it's not going to generate a significant amount of fines. Now the HPGR circuit is really where you started seeing a lot of work getting done. So if you look at the entire circuit feed that we have here, which is the purple line here, and you look at the circuit product that was coming out the green line, now we see a significant shift in the product size to minus 10 millimeter. We're making a lot of minus 1 millimeter in this case. We're starting to generate more of that minus 300 microns, 15% in the case of this HPGR here. So the HPGR with pack bed crushing, getting a small amount of attrition of those particles is starting to make some of those finer products, that are going to go directly to the final grind size. So all this then leads into the ball mill circuit. And you can see here fresh feed was 7.5 millimeters, and they were grinding down to 100 micron size. So a relatively large reduction ratio through this circuit. Relatively high recirculating loads is what they found inside of this circuit here. But they were able to grind down to their final size, even though they had high recirculating loads and they were using a significant amount of power. So this was the base case. This was the survey that was done at the site. Now we start looking at the optimization of it, and we find that, okay, We have two 750 kilowatt secondary cone crushers, so 1.5 megawatt available, and we were only using about half of that power. So you could use more of that power by going to smaller aperture size and reducing that transfer size going to the HPGR circuit. So looking at decreasing this aperture size here and moving to the left on our horizontal axis is going to have benefits downstream. Another thing that was considered then was, if I'm increasing that recirculating load and getting to a smaller aperture size, can I keep that recirculating load and that load on the screen similar? And I could do that by changing the close side setting on the machine. And we were able to do that because we had spare power available on the crushers and spare room to use that up. And typically speaking, when you look at the efficiency of this comminution, single particle compression breakage is about as efficient as you're possibly going to get, because almost all of the energy that you're inputting into that rock goes toward that fracture. Very little losses inside of there, especially when you consider it compared to packed bed crushing or grinding especially. So using more power at this stage is going to be the most efficient. And this is what it comes down to in the raw numbers here. By going from the base case to the maximum target, decreasing that transfer size from 40 millimeter P80 down to 30 millimeter P80, it results in 55% more power draw coming from the secondary crushing stage, which seems like a big number, but when you start looking at it, just the total amount of megawatt that's being used, it's a relatively small difference compared to the HPGRs and the milling circuits. Now we get to the HPGR, and this is a bit wider of a range for this optimization. You can see the base case here was running at relatively low pressure, low specific force, and a 10 millimeter aperture size. So there was room to do more with this HPGR circuit, as evidenced by the 7.2 megawatt that was being consumed. So there's two ways you can start to consume some of that power. And one is to go to a smaller aperture size, decrease that transfer size, and also to run at higher specific force and try to get more of that crushing through the HPGR in one pass. So you can see the trade-off here of going to higher specific force. It starts to take up more power on the machines. And as we go to smaller aperture size, increases recirculating load, but decreases that transfer size going to the crusher, you'll also start to use more power there. So if you look at the combination of aperture size and the specific force, you can start to get a good understanding about what's possible in that circuit. And if you want to quantify it, you can basically do the same capacity in this case study here. Same capacity through the circuit with the same feed tonnage going to the screen. So very similar recirculating load through the machine by increasing the specific force of that HPGR and decreasing that aperture size. So going from a P80 of 7 millimeter to the ball mills down to 3.5 millimeters with the ball mills was possible without significantly increasing that recirculating load. And that's because we had room on the HPGRs to be able to do more work, to run with a higher specific force. So you got a finer product size out, reduces your recirculating load, even though that aperture size was decreased. And again, it's a big number. It's 44% more power in this maximum target scenario compared to the base case. But when you look at it holistically, it's an increase of about 3 megawatt that's consumed in the HPGR circuit. So if we look at how this power is distributed throughout the entire circuit, you can see here it's very heavily shifted toward the ball mills. So the ball mills had 66 megawatt installed on them, almost 15 megawatt installed on the HPGRs, and very little for the crushing circuit itself. So when you start looking at percentage values here, a 50% bump in power on the secondary crushers is very minimal effect on the total power distribution on the circuit, whereas even a 10% reduction in the power consumption at the ball mills is going to have a very significant effect on the total energy usage of the circuit. So let's look at this in graphical form here. The green line here is the energy consumption of the crushing circuit. So that's primary, secondary, and HPGR. And the red line is the energy consumption of the ball mills. So as I decrease this transfer size to the ball mills here, move to the left, I put more load on the crushing section, but the crushing and the HPGRs are more energy efficient. So it's a relatively modest uptick in the power consumption at that circuit. Whereas if I look at how that reduces the energy consumption of the ball mills, which also can be tied to the media consumption of the ball mills as well, I see a much more significant drop because there's a lot more gain to be had by reducing that ball mill power consumption than by increasing the power consumption of the crushing stage. And the overall resultant here is the orange line that sits on top. So you can see as I reduce that transfer size to the ball mills, that the total power consumption is slowly decreasing throughout the circuit. So the base case here is over on the far right. We're using 10 megawatt for the crushing circuit, getting down to a transfer size of 70 millimeter. That means that the ball mill needs to consume 60 megawatt to do the final grind from 7 millimeter down to 100 micron. And the total power consumption there would be 70 megawatt. So now if we look at the optimized solutions, kind of that maximum optimization to that 3.5 millimeter transfer size, I decrease that transfer size in half. So I'm doing twice the reduction ratio through the crushing circuit, which does increase the power, but it only increases the total power of that circuit by 4 megawatt. And what does that do to the ball mills? Well, it drops the total ball mill power consumption to 49 megawatts. Remember, in the base case, it was 60. So it's a significant drop in the power of those ball mills. And overall, it ends up being 62 megawatts. So a 12% decrease in power consumption through the entire circuit based off of transferring where those fines are produced. A little bit more finer product coming from crushing, less work that needs to be done in the grinding circuit. And here's just a quick table that shows the split between the crushing circuit and the milling circuit. And you can see that a modest increase here in the crushing section of the plant has a very significant effect in the energy consumption at the mill, and a total reduction of 8 megawatts going between there. Now, one thing that needs to be considered in a lot of these studies of transfer size and doing more with HPGRs and cone crushers is that there is a cost to material handling. So there's going to be a cost associated with increasing recirculating loads in order to get a smaller transfer size going to the ball mills. That was considered in this study as well. And what they were able to do was increase that specific force to keep that recirculating load pretty similar to what it is in the base case, where it wasn't a significant difference in the energies of that material handling system. But in some cases, they're already running at high specific force, so they don't have that ability to get a finer crush one pass through the HPGR. So the recirculating load is going to go up, and there is going to be a cost associated to that material handling. We can talk a little bit more about that in a bit. With that, though, I want to talk more specifically about HPGRs. So I am going to hand it over to Alan.
Thanks, Dusty, for a great review there. As Dusty said, I'm going to speak a little bit about fine crushing in the Metso Outotec HRC HPGR. I'd like to spend just a couple of minutes talking about not just the efficiency of an HPGR, which I think most of us are pretty familiar with these days, but how the HPGR can be made more efficient by the introduction of flange technology. So why is flange technology important? Well, flange technology is important because it helps us to eliminate or reduce so-called edge effect in HPGR product. Edge effect is essentially the phenomenon where we get a coarser material being produced from the edge of the HPGR rather than from the center. And that is, in effect, due to the fact that you will get a higher pressure in the center of the HPGR than you will on the edges. So what does edge effect do? It means you get a coarser product size. You get an uneven wear on the tire surface. So in a lot of cases, what you will see is a so-called bathtub-shaped wear profile. And obviously, it will reduce your energy efficiency. So Metso overcame this problem by inventing the HRC HPGR, which incorporates flange technology. So we can look at the difference between a traditional HPGR on the left and a Metso Outotec HRC on the right. In a traditional HPGR, material is held in between the rotating rolls by cheek plates that are placed on the sides. What happens is that as the material is being pulled down through the HPGR, these cheek plates provide a static friction surface, and that essentially prevents material from going down through the edges of the tires. On the HRC HPGR, on the other hand, because we have flanges on one of the tires, as these tires are rotating, those tires are actually doing the opposite. They are pulling material down through the edges of the tires. So what does this mean in practical terms? Well, it means that as we're able to move material through the crushing zone at the edge of the tire, we get higher crushing forces at the tire edge, and we're also able to achieve a higher force profile across the entire width of the tire. So a more even pressure profile means more energy efficiency. So that was the idea that we had on paper many years ago, and we were lucky enough to work with Freeport-McMoRan and their expansion at their Morenci concentrator in Arizona. And in this expansion, we built a pilot 800 millimeter diameter HRC to test the concepts. And we did over 114 different process surveys over about a year and a half. And what you're looking at here is the results of two process surveys where essentially everything else was equal, except on this particular HRC, we ran one test with traditional cheek plates, and one test which is the orange line, and one test with flanges, which is the green line. So what you're looking at here are the feed conditions for the two different tests. And what you can see in this next slide is the product coming from the edges of the tires. Very clearly, the product on the with the flanges is a much finer product, and you can see that straight away without even having to go to the lab. These are shots from the sample buckets directly underneath the HRC, where we are able to sample the edge and the center product independently. And in terms of overall product, when we add the center product back in, what you find is that everything else being equal, and so that's specific force, that's the screen apertures, the material that's going in, we get a 1.5 millimeter reduction in P80 by adding flanges versus having cheek plates. So in total, over 14 different surveys that we did where we were specifically focusing on flanges versus cheek plates, what we found is that at the HRC 800, which has a 750 millimeter diameter tire, we were able to reduce the specific energy by 13.6% compared with a cheek plate design. We were able to reduce the circulating load by 24% and increase the specific throughput by 19%. Obviously, these are going to have significant implications for the design and operation of larger scale HPGR units. And I will summarize the findings here for you a little bit. So what we see is with the HRC, operating with flanges means increased breakage rates, which provides higher energy efficiency. We also get a higher specific throughput, which means increased unit capacity. In other words, more material through the same size of machine. Even crushing force reduces the tire wear. So instead of having that bathtub tire wear, because we're able to keep that wear profile completely even across the width of the tire, we get a more even wear profile and we get a longer tire life. In open circuit applications, this allows us to produce a finer product in an open circuit, and that this can be useful in things like a heap bleaching operation, for example. And then in closed circuit operations, what this means is that we can run reduced circulating loads, and this has a big impact on your auxiliary systems, for example, your conveyors and your screens and your apron feeders in the rest of the system. So I'd like to take a few minutes to go through a couple of case studies to show exactly how HPGR works in the field. The first study is the FMI Metcalf concentrator. This was published by George Zervas from FMI at the SAG 2019 conference last year. At the FMI Metcalf concentrator, Metso has a pair of MP 1250. Those are 1,250 horsepower cone crushers in secondary duty, and a single HRC 3000. This is a 3-meter diameter HPGR, and it is in fact still the largest HPGR in the world. This circuit is very much like the case study that Dusty showed you earlier, where we have a primary crushing circuit, we have closed circuit secondary crushing, a closed circuit HRC, and closed circuit ball milling. Across all these surveys, the specific force was varied to evaluate the performance of the HRC. And in general, what we found was that as the specific force increases, the circulating load decreases and the fines production increases, which makes perfect sense. As you put more force into a rock, you're naturally going, especially in a compressed intraparticle comminution like Dusty was talking about, you're going to create more fracture planes and you're going to create more fines. As you create more fines, you're going to have a better efficiency on your screen, so more material is going to pass through your screen after each pass through the HRC, and your circulating load is going to decrease. So again, this table is taken directly from the Zervas paper from SAG 2019, and what this shows is that as the specific force increases from 2.5 to a little over 4 newtons per square millimeter, no matter what size class we're talking about, we do see a slight increase in the amount of particles in that size class that are being created. So again, as specific force increases, the amount of fines tends to increase. I'd like to take just a minute to look at just a couple of the surveys in a little bit more detail. I realize this might be a little bit hard for you to read on the screen, but here we can see exactly what the circuit looks like, where we have a secondary cone crusher in the top left in closed circuit with the screen. That is feeding a single HRC 3000, which is in closed circuit with screens as well. In these two surveys, we're looking at a case where we have a specific force of about 2.5 millimeters on the low newtons per square millimeter on the low end, and a specific force of about 4.1 newtons per square millimeter on the high end. The fresh feed size is pretty similar. It's a little bit coarser on the low end than it is on the high end, but they're both about 25 millimeters as a F80 to the HRC circuit. What we see, though, is that as this specific force is increased, the HRC product goes from 12.5 millimeters to 9.3 millimeters. So we are in fact creating a finer product out of the HRC by increasing that specific force. But something interesting is happening here. We have the same screen aperture on both surveys, but what happens to the wet screen undersize is that our screen undersize actually goes up by a little bit. And how can we explain that? Well, it's fairly simple. Is that as we are creating more fines in a single pass through the HRC, that screen is becoming more efficient. So more of that material is sub 8 millimeters, so it's getting through the screen in the single pass, and our circulating load is dropping from 54% to 34%. And what that means is that the HRC is getting fewer passes at each rock as it's coming through. So in fact, even though our product from the HRC is getting smaller, our product from the circuit is the same or getting a little bit coarser, which leads to what Dusty found in the previous study, which is the course of action here would be, if you have room on the speed and on the power in the HPGR, would be to decrease that aperture size on your screen in order to produce a finer product going to your ball mill. So what does all this mean in terms of impact on the downstream process? Well, it means that an HPGR HRC is going to give you pretty flexible control over your product. You can dial the specific force into whatever range you need, depending on the ore properties that you're looking at. And with a little bit more trouble, you can obviously change the screen apertures to really dial in and optimize your primary grinding circuit or your tertiary crushing circuit, however you want to think about your HPGR. And really what this means is that efficient combination with the HRC HPGR, or any HPGR, can allow for less intensive energy requirements for downstream grinding. There's been a great number of studies that have suggested reductions in operating work index of 10 to 15% in downstream ball milling when you're following an HPGR. And this is often attributed to the presence of microcracks in the HPGR product. That is, small cracks that are left over in the product that create natural breakage planes for the ball mill to act on. Of course, I'd be remiss if I didn't say that there are some people that say that the reduction in operating work index is primarily a result of having a relatively fine particle size distribution coming out of the HPGR, but the result is still the same. To get to the P80 final product size out of your grind that you're looking for, you do require less energy after an HPGR. I'd like to take just a couple of minutes to take a look at yet another SABC versus HPGR trade-off study. This one was, just to put a little bit of a financial context around what we're talking about, this one was a large-scale production project in South America, a gold project that had very hard ore, an 8 times V at 26, and a bond work index of over 17 kilowatt hours per ton. The base case design included 3 40-foot diameter SAG mills that had 25 megawatt GMDs. There were 3 operating and 1 spare MP800 pebble crushers. And then finally, the grind was finished up with 3 26-foot ball mills with 18.5 megawatt dual pinion drives. So obviously the objective of the study was to evaluate the potential for CapEx and OpEx reductions by replacing the SABC circuit with a 2-stage closed circuit crushing HPGR and ball mill circuit, just like we looked at in the previous couple of examples. Let's fast forward to the good stuff instead of looking at flow sheets. In the top table, what you can see is the net power requirements and the specific energy requirements for the base case SABC circuit. And immediately what you can see is that the bulk of the energy required in that circuit is represented in the SAG mill, so about 11 kilowatt hours per ton. The rest of it is mostly located in the ball mill, another 8.2 kilowatt hours per ton, with a small contribution by the SAG discharge screen and the MP800 pebble crushers. So in total, you're looking at about 19.5 kilowatt hours per ton in order to go from primary gyratory product through to the primary grind. When we replace that SABC circuit with an HRC ball mill circuit with secondary crushing, what we see is that if we make a parallel between the SAG mill and the HRC as being your primary grind, there's a massive reduction there of about 7.8 kilowatt hours per ton in order to achieve that primary grind. Now, the transfer size to the ball mills is a little bit coarser, so we end up using about 1.2 megawatts more in the ball mill. But that first reduction in the HRC is easily providing enough energy savings to pay for that small reduction in the ball mill and the relatively small increase in energy in your secondary crushing circuit. Now, one thing to notice here is that, as a matter of course, when I do these studies, I do add a material handling net power, and as a rule of thumb, I use 1 kilowatt hour per metric ton. So I've added about 6.2 megawatts to my power table here in order to account for all the material handling around the secondary crushing circuit and the HRC circuit. Nevertheless, what I come to is a total specific energy of about 14.1 kilowatt hours per ton, which represents a specific energy savings of 28% over the SABC circuit. When we put some numbers around that and we think about electricity or power at 7 cents per kilowatt hour, what we end up seeing is that we are going to save about $14 million per year just in electricity or power savings versus the SABC circuit. But interestingly, that's not your biggest savings. Your biggest savings is actually in your media consumption. The HRC, unlike the SAG mill, obviously has no media to consume. So you're getting rid of that entire big sink of costs in your operation. Because the HRC tends to have relatively long wear lives. In this case, we're estimating about 20,000 hours on the tires. The wears and spares are actually pretty comparable between the two, but you are going to spend a little bit more in your labor costs to affect those regular maintenance activities. In total, what we see is about a 76 US cent per metric ton reduction in your comminution cost from going from an SABC to an HRC ball mill circuit. Now, when we look at CapEx increase, and yeah, I did say increase because what we often find is that when we go to an HRC ball mill, there is usually a bit of an increase in total installed cost versus an SABC. And that's really just due to the complexity of the circuit. In this case, we were looking at about a $60 million total installed cost increase. But what is interesting is that the direct equipment cost here is not what's driving it. The direct equipment costs are actually a little bit lower. And that's primarily due to the fact that if you'll recall that these 40-foot diameter SAG mills all have 25 megawatt GMDs, and those GMDs are both expensive to buy as well as expensive to install. The ancillary equipment factor that I have here, I doubled for the HRC, and really what this takes into account is all the material handling, the conveyors, the apron feeders, the dust handling, all those things that you're going to have to add into a HRC ball mill circuit relative to a SABC circuit. But overall, what we end up with is about a $60 million difference in total installed cost. When we look at that on a 10-year NPV basis, what we find is that we get about $160 million in energy savings, another $150 million in media savings. We will spend about another $60 million at year one or year zero on the CapEx. But overall, over 10 years, the change from SABC to HRC ball mill results in a savings of over $250 million to the project. Finally, I'd like to have a moment here to get you to think a little bit laterally about what HPGRs can do. We did some significant test work a couple of years back looking at a project where we wanted to dry grind to a pretty fine particle size with HPGR. And in this case, what we were looking at was a two-stage HPGR circuit with classification between the stages. Now, the reason why we wanted to, or the customer wanted to do it this way, is that, number one, it was a fairly low throughput material, but they had diesel power as their only power source, and that was at about 35 cents a kilowatt hour. So very expensive power, which means that energy was very important. They also had to keep the product dry for shipping reasons. The product specification at this point was 98% passing, 250 microns. But the other goal was to minimize the amount of minus 75 micron material that we were creating. So as I mentioned, we did quite a substantial amount of test work in our lab in York, Pennsylvania. We did closed circuit HRC 300 test. The HRC 300 is a 300 millimeter lab scale machine, and we closed that with a 850 micron Rotec screen. We did lock cycle HRC 300 tests with a 250 micron Rotec screen, and we also did some air classification tests. But what I'd like to call your attention to is the same sort of theme that we've seen in the last 45 minutes or so, is that as we increase specific force, in this case, for example, from just over 2 newtons per square millimeter to 3.7 newtons per square millimeter, our circulating load in this closed circuit test decreases. What you will see is that, and I don't have both graphs here, but you will actually, the reason why you're reducing circulating load is, of course, that you are generating more of that 250 micron material on each pass. So with the data from the test work that we did in Pennsylvania, we were able to build a population balance model and run simulations of the entire circuit. And what I'd like to show you here is again, just some results from that circuit. Here we have the stage 1 HRC 800. What we see, like I said, time and again, is as we go from lower pressure, 2 millimeters, 2 newtons per square millimeter, to 3 to 4, what we see is that percent of material passing 75 micron increases from 19.5 to 23 to 26.6. So time and time again, we see that as we increase the pressure on an HPGR, we do increase the amount of fines. Now, in this case, what our lab work and our simulation showed is that the HRC HPGR actually created too much of the minus 75 micron product with this material. And that was important because that product couldn't be used; it had to be discarded. So we weren't able to put this particular circuit into play. But in circuits where this fine material is not rejected, 2 or sometimes even more stage HPGR with screening or air classification can be an economic solution for dry grinding applications. And with that, I would like to thank you all for sitting and listening to us this morning.